What's up, everybody? Hope y'all doing well. I'm Danny Roy Hampton, and today I'll be talking with you guys about the logistics involved with fuel cell technology. All right, so here we have a brief overview of what I'll be talking about. We're going to start with the fuel cell basics. Before I begin to explain what a fuel cell is, I have to explain how the hydrogen is obtained in the first place. Hydrogen is normally found out in nature by itself. So in order to get pure hydrogen, it has to usually have to put water through a process called electrolysis. So essentially, how this works is that you get an electrolyzer. They use electrical energy to split the water into pure hydrogen and oxygen. Um, so if this electricity comes from a low carbon source like this, the result is often called clean or green hydrogen. So when I'm talking about the fuel cell and its logistical costs, I'm mainly talking about the use of green hydrogen. All right, so here I have a diagram of a fuel cell. A fuel cell essentially is an electrochemical device. Um, it has three components: the anode, the polymer electrolyte membrane, which is in the middle here, this red line, and the cathode. There are no moving parts at the core of it. The only things that do move are the hydrogen gas that flows through the electricity and the byproducts. So how the process goes is that the hydrogen gas flows in through this anode, where there's a catalyst, usually made of platinum. That platinum catalyst rips apart the hydrogen into a proton as well as an electron. The protons, they're able to take a shortcut and go straight through the electrolyte membrane to the cathode side, while the electrons have to take the long way and via this external circuit. So as they're traveling through, they're generating electricity. That's how energy is formed from this process. So when they make it over to the cathode side, there's oxygen in this chamber. So the proton and electron come back together and form hydrogen. Hydrogen forms with oxygen, and the byproduct of that is water. Um, Another byproduct is heat, and like I said earlier, electricity is generated through this external circuit. All right, so in this slide, I'm just going to give you a brief history of the fuel cell and its use throughout time. So it's credited to Sir William Grove. In 1839, he demonstrated the first gas battery that utilizes fuel cell tech. It gained major importance in the 1960s through NASA's use of it in their Gemini and Apollo missions. Also in the 1990s, Chicago made use of hydrogen fuel cell buses in prototype transportation systems. In the 2000s, a company known as Plug Power is scaled in development utilizing forklifts. Walmart and Amazon actually began using this type of tech around that time. In 2020 onwards, you can see now that the infrastructure has grown majorly since then. Um, you can see it in fleet trucks, trains, um, general infrastructure for data centers, and the like. So here I just want to go over some use cases. I already touched on it a bit, but um, yeah, a number of these are dealing with transportation and fleet utilization. So here we have the 2026 Toyota Mirai. Um, this is Toyota's latest fuel cell vehicle that's out on the market. We also have the X-Gen fuel cell truck made by Hyundai. Like I said earlier, Walmart is utilizing fuel cell technology to power their forklifts in warehouse settings. And we have this example here. California actually began using a fuel cell powered train to transport people. And then here's that example from On the last slide, the bus that the Chicago Transit Authority used um, as a test um, for their hydrogen fuel cell fleet. And this is one of the, I would say, major use cases today that fuel cell technology has been used for. It's being rapidly adopted and used for data centers to meet the growing power demand that these types of facilities require. Okay, so in the next few slides, I will be going over the logistics side of the house, starting with the storage. So, hydrogen storage is one of the most constraining steps in fuel cell systems. This slide is highlighting the two main forms of storage with hydrogen. So, you can either use it as a compressed gas, or store it as a compressed gas, or store it as liquid hydrogen. Um, the gas is usually compressed to about 350 to 700 bar, while liquid hydrogen has to be stored at very cool temperatures so it can remain liquid, negative 250 to 3 degrees Celsius or negative 423 degrees Fahrenheit. So the compressed gas is common in vehicle applications, while the liquid hydrogen becomes more attractive for high volume transport via fleet vehicles because it stores more hydrogen in less space. Each method, however, carries trade offs and equipment costs, like with everything, energy demand, and the complexity with the operations. So I just have this slide here to emphasize that safety is also a core part of hydrogen transport or storage. Hydrogen must be carefully managed because it is a small molecule, it can leak easily, and is often handled under high pressure or cryogenic conditions. It's also very flammable, extremely flammable. So safe storage always depends on either strong tank design, leak detection because it is an odorless gas as well, proper ventilation. You need pressure relief systems, and most importantly, proper training because without proper training, none of the things I mentioned earlier really matters. Um, all right, so in this slide, I just wanted to address the three main modes of hydrogen transportation and delivery. So those are the pipelines. We have tube trailers and also liquid tankers. So I wanted to note also that the United States has about 1,600 miles of hydrogen pipeline, and that these pipelines they generally provide the lowest delivered cost per kilogram at scale. Since once the infrastructure is laid in place, there isn't any need for loading up a vehicle or hiring a driver and things of that nature. Um, so the tube trailers they carry compressed gas at roughly 180 to 250 bar, and they hold about 200 to 1100 kilograms per trailer. The liquid tankers themselves they can carry around 4,000 to 5,000 kilograms per truckload because, as I said, um, that is more valuable for more bulk loads since it's more compressed. Um, is able to be more compressed and condensed. Um, but they also require cryogenic equipment, so you're able to transport more, but you also have to add the cost of cryogenic equipment to that. So one of the most important takeaways here is that the delivery can add about $1 to $5 per kilogram on top of production costs. Um, so having these numbers make sure everything is squared away with the delivery method and the equipment is key to ensuring that you get the most out of what you're spending to transport and deliver this resource. In this slide, I'm just giving more of a comparison on the efficiency of fuel cells versus battery electric vehicles and diesel and gasoline vehicles. Um, so, fuel cell vehicles, um, they tend to have about a 60% electrical efficiency. Battery electric vehicles are sitting around 90%. Um, Gasoline have about a 20 to 40% thermal efficiency. So, as you can see, battery electric vehicles still have an advantage against f- fuel cell electric vehicles. Um, about a 30% gap there. Moving on to the tailpipe emissions, obviously fuel cells and battery electric vehicles will win in that regard against diesel and gasoline. Um, the only byproducts, as I said earlier, for fuel cell vehicles are uh, water and a bit of heat, along with the electricity generated. Um, so going on to the refuel and recharge section, um, fuel cells actually beat out battery electric vehicles, taking around 15 minutes or less to refuel, while the battery electric vehicle has to take a lot longer. Um, Diesel and gasoline, obviously, it only takes um, a few minutes at the pump, 5 to 10 minutes on average for those um, larger fleet vehicles or big rigs. Um, the range, um, fuel cell vehicles are actually very competitive with electric and gasoline. Um, the average cost for a hydrogen fuel is actually twice the amount of diesel, um, using diesel as the baseline. Same for the battery electric vehicle. It's actually 3.5 to 5 times more costly than if you were to just use a diesel to um, fuel that vehicle. So overall, as of today, the best fit for fuel cell vehicles can be seen in um, long haul fleet operations, anything concerning um, heavy duty work. All right, so here I have an example straight out of St. Gabriel, Louisiana. Um, so Plug Power and Olin Corporation, they started a 50-50 joint venture supported by the Department of Energy, which gave them a roughly $1.7 billion loan to begin. Um, they started it in 2022 and began running just last year, Q1 of 2025. So they're able to produce about 15 metric tons of liquid hydrogen a day. They have a total capacity of 40 tons per day. Um, so the hydrogen is sourced from a process in Olin's chloralkali manufacturing process, and their key customers, like I said earlier, how Walmart is utilizing um, forklifts in their warehouse operations. So is Amazon as well. Just a quick note before I get to the next few slides. I did want to make a note. So the hydrogen fuel cells by themselves, they don't produce enough energy. They have to be put together in a series, usually known as stacks, to be able to produce enough energy or generate enough power for operations. All right, so in this slide, I'll be getting more into the economics of fuel cell delivery and production. And with these things, the terminology used is normally in either kilowatts, um, dollars per kilowatt, or weight by day. So for the PEM system, it costs roughly around $108 per kilowatt for an 80 kilowatt system at high volume. The stack, like I mentioned earlier, costs about $67 per kilowatt, with the baseline system costing roughly $8,640. Um, so that's that total 80 kilowatt system baseline cost. I will note that the Department of Energy has a target price to get the cost of it to $4 per kilogram. Um, so it can be so the fuel cell electric vehicle can be competitive in the um, diesel and natural and gasoline market. So just moving down this list, you can see it for yourself. Distributed natural gas stations, they usually cost around 1,500 kilograms per day for distribution, um, which roughly comes out to $8 to $10 per kilogram. Um, for fuel cells, distributed electrolysis stations, as you can see, the cost jumps up a bit to $10 to $13 per kilogram for distribution. Um, so threshold the comparison versus gasoline. This was in 2020. It's $2 to $4. The gasoline per gallon equivalent. So there's a difference there. So moving on down past that competitive threshold, as you can see, the NERL mid-range hydrogen price, their assumption is to be around $7 per kilogram. Like I said, they're still looking for that low range price. The target is $4 per kilogram. Um, and here's the part that will probably be paid attention to the most is how much the operation and maintenance costs will be per mile. So, Class 8 fuel cell electric vehicles, they're coming in around 6 cents to 15 cents per mile, while Class 8 diesel vehicles um, are merely at around 8 to 30 cents per mile. Um, a lot of that cost comes from just the general maintenance that goes into all the moving parts in a diesel vehicle. So here I just wanted to highlight what is still today one of the biggest contributors of the cost of using a hydrogen fuel cell, which is platinum. Um, Platinum is still used today because it is still one of the best catalysts used in a hydrogen oxidation and reduction reaction. Um, it may account for about 40% of that polymer electrolyte membrane system I talked about earlier. It gives today platinum is sitting at around $1,800 per ounce. This was as of June 15th of 2026. Um, so they're showing progress in reducing catalyst loading, including reductions from about zero point 0.5 to zero point 0.2 grams of platinum per kilowatt. But still, even with that improvement, it still remains the leading bill for materials used in the production of hydrogen fuel cells. So here I'm going to talk about one of the most promising research developments for lowering the cost of the fuel cell. Like I said earlier, if you remember, the platinum catalyst tends to be the biggest driver in how expensive fuel cell is to operate and maintain. So um, there's a study in 2026. They use from multiple institutions on the use of iron-based um, iron, nitrogen, carbon catalysts, um, including improvements to turnover, the frequency, also the oxygen reduction selectivity, the durability, and the energy density under laboratory conditions. Um, it included that the platinum-free catalysts are approaching platinum-like performance in the lab, but still not quite there. Um, but with further research and further technological developments, they projected to potentially get there within the next 3 to 5 years. So if that comes to fruition, then It's possible that the cost to build and operate a fuel cell stack could be driven way down. All right, in this slide, I'm just giving a general outlook on where we are versus where we are headed with fuel cells. Um, the first 2 points basically already hit, so mainly going to talk about this expected growth section here. So the fuel cell electric vehicles, the total cost of ownership, um, parity that they're looking for as possible within this time frame that we are in now, probably leaning more towards the 2030s. Um, and the Department of Energy still has a target to accomplish having $1 per kilogram of clean hydrogen um, in production costs by 2031. And here I have my list of references. So I want to thank everybody for taking the time to watch this video. Hope you learned something. I definitely did throughout the making of this, and very hopeful for the further development of this type of technology. I think it's very interesting. Thanks.